Okay, so one of the challenges that we're facing in this first chapter is that I'm trying to just give you a rough idea, but there's so many different things we could spend time on that we could really spend the whole course just introducing everything so that I can speak as clearly as possible. But I think I am going to talk a little bit about what space-time symmetries are and what internal symmetries are, because you might not have seen them. So let's just talk about what is a space-time symmetry. So a symmetry is always associated with a transformation, and space-time symmetries are transformations that act on uh, the points of space-time. So because of that, they end up uh, the rule for the transformation mixes fields at different points. Um, so let me give you an example. Okay. And so here's an example. Let's think about a Lorentz transformation. So under a Lorentz transformation, x mu goes into x prime mu, which is lambda mu nu x nu. And lambda would be the matrix representing the Lorentz transformation. Then the transformation rule for the field, let's just say we've got a scalar field. So phi would go into phi primed of x primed, and this would be equal to phi of x. So what you see in this rule, in the red box, is that I'm talking about fields at phi primed and phi, fields at x primed and x. So that's what I mean that it mixes fields at different, let's say, space-time points. Different space-time points. That's what I mean. Inside this box, the rule is equating phi primed at x primed to phi at x. If, however, you look at an internal symmetry, well, an internal symmetry does not act on space-time. Does not act on space-time. So let me give you an example of that. We might consider a U1 phase rotation. So phi of x goes into phi primed of x, which is e to the I alpha phi of x. So what you can see now is the rule for the internal symmetry related the field at x to the field at x. Okay? So that is just what we mean by a space-time symmetry and an internal symmetry. And the Coleman-Mandula theorem uh, provides a restriction on what space-time symmetries you can have. You can have as many internal symmetries you like. Coleman-Mandula is not restricting the internal symmetries. It's only restricting the space-time symmetries. Now, it turns out that there is a loophole in Coleman-Mandula theorem. So you can get around the Coleman-Mandula theorem. There's a loophole in Coleman-Mandula. Now, this is a theorem, so the only way that there could be a loophole is if there was and one of the assumptions that you made when you proved the theorem was wrong. And in fact, one of the assumptions was too strong, it can be weakened. This was pointed out by Haag, uh, Lapozansky, and Sonius. So there is a Haag-Lapozansky-Sonius theorem. And what they did, what assumption of Coleman and Mandula did they weaken? Well, Coleman and Mandula assumed that if you perform a symmetry transformation, it'll never turn a boson into a fermion. And Haag, Lopozonsky, and Sonius said, well, maybe our space-time symmetry transformations can turn bosons into fermions, so maybe there's some supersymmetry, and they were able to prove that the biggest space-time symmetry, so let me just say space-time symmetry is supersymmetry. So super Poincare invariance. So I'm not going to say any more about supersymmetry. Maybe we'll do a course on that at some point. But for now, I'm just going to tell you that that's the biggest symmetry that you can have is supersymmetry. Now, at this stage, I think you must be puzzled. You should be objecting. And the reason why you should be objecting is this course is all about CFT, but in CFT, you also have a scale symmetry. This is something that we've stressed a few times in our discussions. But how does scaling act on the space-time coordinates? Well, it does act. X mu goes into lambda x mu. So that means conformal symmetry is a bigger space-time symmetry than Poincare invariance. So it's inconsistent with the Coleman-Mandula theorem. Why is it inconsistent? Well, in fact, there's no contradiction. So there's no contradiction with Coleman-Mandula, with Coleman-Mandula. But, and the reason for that is that in CFT, there is no S matrix. When you try to define an S matrix in CFT, you get all sorts of infrared divergences that happen at very, very low energies. And they basically happen because in a CFT, you must be dealing with massless particles. If your particles have a mass, that sets a scale. So CFTs are always theories of massless particles. And for that reason, there is no S matrix. Now, this is something to pay attention to because often in quantum field theory, the basic observable, the most important observable, where almost all of the physics is contained, is inside the S matrix. So in quantum field theory, you would spend your life calculating S matrices and comparing them to the results of scattering experiments, like the kind of data that comes from the LHC. And here I'm telling you there is no S matrix. So you should ask what it is that you study in CFT. In CFT, the thing that you're really always interested in is correlation functions. And you're interested in computing correlation functions the whole time. And in fact, so we're going to calculate lots of correlation functions too, figure out how to do that. But because of this, now you can actually formulate a different kind of a theorem. And this is something that was formulated by Maldacena and Zibodev. And what they proved, so it was a statement in 3D CFT, okay? I'm not sure if you can prove it for other CFTs in other dimensions, but certainly in 3D CFT, what they proved was conformal symmetry. Conformal symmetry is the most amount of symmetry you can have if your correlation functions are non-trivial. So what do I mean by that? If you have more than conformal symmetry, you can prove that your theory's correlation functions will always be those of a free theory. So if you don't want correlators of a free theory, then the maximum amount of symmetry you can have is conformal symmetry. And that motivates us in this course to study conformal symmetry. This is, in a sense, the biggest amount of symmetry that we can have. Okay, so we've set the stage. This is the end of the introductory chapter. Now, let me just make a few comments. I hope you're not feeling too frustrated. I have chosen to pick up physics from all kinds of areas for this discussion. I haven't been systematic and I haven't explained every single thing that you've needed. So there's been places where there's been holes in my discussion, And those holes have been there. It's necessary because I just wanted to give you a big bird's eye picture of CFT. But from now on, we're going to be systematic in our discussion. We're going to do everything. There's going to be no holes, and I'm going to try to explain everything perfectly. If there's something in this first chapter that I explained and you're particularly interested in, but you don't understand, please do come and chat to me. Just come knock on my door and we can talk about it. Or you can send me a WeChat message if you want to ask a question that you think is a short question. That's also perfectly okay. And I hope I've given you the keywords that you could go away and look in the literature and check on the internet and get relevant material. But don't despair if you're feeling at sea. I didn't expect you to understand everything perfectly, but from now on, I do. So from now on, every single thing that we discuss, I expect that you understand it perfectly, and I'm going to do my best to make sure that my explanations don't have any holes in it. This is such a beautiful subject, and I really want you to understand it perfectly.